Okay, hello everyone. It is 7 p.m. Eastern, and that means it's time to begin our CoCoRaHS webinar. Thanks for joining us today. I'm your host, Noah Newman. I'm the Education Coordinator here at CoCoRaHS headquarters. We are coming to you live from the Colorado Climate Center here at Colorado State University in sunny and hot and red flag warning and smoke is visible and in the sky here in Fort Collins, Colorado as we speak. CoCoRaHS is sponsored by grants from NOAA's Office of Education and the National Science Foundation. Today we are hosting a special webinar with guests from NASA, the University of Illinois, and the Iowa Flood Center. They will introduce us to the NASA Global Precipitation Measurement Mission, and we'll be talking about their ongoing Iowa Flood Studies field campaign. So let's begin by introducing Dr. Dalia Kirschbaum. Dr. Kirschbaum is a physical scientist in the Hydrological Scientist Laboratory at NASA Goddard Flight Center, and is also the GPM Application Scientist and Education and Public Outreach Coordinator. Dr. Kirschbaum's research, she focuses on rainfall-triggered landslides and how these processes can be modeled and assessed using satellite information. Dr. Kirschbaum, can you hear me?
Yes, I can.
Great. Let me get your PowerPoint loaded here, and we will begin momentarily.
Excellent. Well, thank you all for participating in this webinar. We are very excited to share with you this upcoming mission, the Global Precipitation Measurement Mission, as well as a fantastic field campaign that is currently underway and providing tremendous data that will help not only improve global precipitation, but really help to understand and improve our measurements over the globe. So I'm just going to provide a brief overview of what we have in the pipeline. And if we could just go to the next slide. So what we're really talking about, why do we need to measure precipitation? Well, I'm preaching to the choir a bit here, but the reason why, we need to sense precipitation not only in our backyards, but to provide a global view is to really understand how we can move from feeling precipitation locally to how it interacts with global weather patterns to move heat and energy around the planet. Now, in order to understand precipitation's movement in terms of the quantity and character, it's really important to understand its impact on streams, rivers, surface runoff, and groundwater. We also need to understand how precipitation varies both in space and time, so we can estimate into the future how precipitation might vary in a changing climate. You can see on the graphic, we don't have a very direct way to measure latent heat release and exchange in the atmosphere, and so precipitation allows us to really observe those phenomena and, as you see, move precipitation from the equatorial region to the subtropics and the polar areas. So understanding that heat distribution is vital. We need to vitally understand precipitation. And then we need to understand our freshwater resources, agricultural production, both looking within our backyards as well as at regional and global scales. So with that, I'm going to attempt to show a video. If it doesn't work, then the URL is right there, along with many, many other exciting educational videos about GPM. But let's give it a shot. Okay, I'm not hearing any sound. But it looks like we might not have any sound for this. So I'll tell you what, let's move to the next slide, if that's okay. Perfect.
Sure, and Dalia, sorry about that. I'm not sure why sound has not come through, but the video was coming through beautifully. So,
it's a teaser. Please go to the website. We did it on purpose. Please go to the website and check out not only this video, but many, many others that we have been developing in preparation for this mission. And we will provide a little bit more on our education and outreach efforts with Dorian a little bit later in the webinar. But for now, we're going to go to our first question, and it is, how does the GPM satellite, the Global Precipitation Measurement Core Observatory satellite, differ from traditional weather satellites? A, are they the same thing? the GPM satellite orbits at a lower altitude. GPM instruments can directly measure precipitation droplets. GPM has different instruments to measure precipitation. B, C, and D are correct, or I don't know.
Okay, so I have launched the poll, and everyone has a choice between A, B, C, or D, or E, and many are voting, and I'm going to give it about 5 more seconds and close it. All right, so we'll close this here, and now I'm going to share it. Dahlia, are you able to see the results here?
I am, and the 63% of you are correct. Though I guess pretty much all of you are correct in some way, shape, or form, because they are not the same thing. So well done. Now, the reason that I bring this up is because we get this question a lot. NASA is a research institute, and the goal is to expand our understanding of precipitation from the microphysical level all the way to the global picture. Now, just to answer the question very briefly, you can go to the next slide, perfect. Weather satellites, are traditionally geostationary in orbit, and it means they orbit at about 42,000 kilometers or 26,000 miles up, and they are able to look at the same place on the Earth all the time. And they look at the energy being emitted from the clouds, the temperature of them, and they can infer precipitation. Now, there's other satellites like polar orbiting satellites, the NPP is an example here, that orbits right over the poles and has the same crossing time at the same time of day. And that's at about 820 kilometers or about 500 miles up. Now, the difference, if you just click one more, between what we're talking about and let's say the geostationary satellites is TRMM, which is what's currently up now, is in what's called a non-sun synchronous orbit, which means that it orbits the Earth going from about 35 degrees north, kind of the sort of top of the U.S. To the kind of southern tip of South America, and it is able to look at taking different diurnal measurements, meaning that you can look at the same place at different times of the day, and that's really important for understanding the different precipitation processes that we can observe throughout a 24-hour period. Now, the TRMM satellite, the Tropical Rainfall Measuring Mission, was launched in 1997, and it's been providing data for over 15 years, almost 16 years, and it has been extremely successful to measure both three-dimensionally through the clouds, as well as to get a sense of what we're observing using microwave information, and we'll get into that a bit more with Walt and Steve's presentations. So just to give you an example, TRMM is the first time that we've ever seen three-dimensional cross-sections of storms, and this is an example from some of the observations from tornadoes that we observed. The red is really, really intense precipitation in the clouds. So if we go to the next slide, now TRMM has, as I said, been up for over 15 years, and GPM will continue the measurements of TRMM, but we'll have 2 more or 3 more advanced instruments. And the difference is it'll have a microwave imager, which uses microwave information and others to look at 13 different channels of energy that's being emitted from the precipitation. So we're able to look at everything from light rain to heavy rain and falling snow. And then we'll have a true frequency radar. Just like we see a radar gun from a policeman, it sends out a signal and you get a signal back. Well, the scattering off the droplets, which again, Walt and Steve will get into, allows us to say what is in the atmospheric column. And this is a really unique aspect. It's a very different set of instruments than we have on different satellites, and it allows us to get a much better picture of what we're observing in precipitation. So if you go to the next slide. Now, another really interesting aspect of this mission is GPM is not just one satellite. It's actually an international mission that's using a combination of about 8 other satellite information to get an improved space and time coverage of precipitation, rain, snow, and the like. Now, it's going to be providing a global data set every 3 hours, and it's orbiting in a little bit higher altitude. So GPM will go from the Arctic to the Antarctic Circle. Now, if you click one more, the other thing is that this very international mission in nature has satellites from international and domestic, from NOAA, from the Department of Defense, Europeans, India, and France. And they also have project investigators from 13 other countries that are helping not only with this, with providing satellite measurements, but also a ground validation network that we're going to be talking about with iFloods. So if we go to the next slide, we're going to have my second question, which is, why do we need 3-hour data? How can it be helpful? So GPM will provide precipitation data every 3 hours to be read on the local evening news, to help understand and forecast extreme events, to replace other satellites, or for tracking the jet stream. So.
Okay, I've launched the poll. We've got folks responding. We'll give you a few more seconds here as everyone gives us their best guess. And we'll go ahead and close that and share the results.
All right. So the answer is to help understand and forecast extreme events. Now if we go to the next slide, I will explain that. So, the Global Precipitation Measurement Mission and TRMM already provide amazing capabilities for a large array of applications, and GPM will help to extend those applications. We need accurate precipitation information to understand flooding and flood modeling, landslides, which is my area of expertise, to understand freshwater availability and then agriculture, so you need accurate crop models which require precipitation inputs. In many areas of the developing world, we really have no local networks to do that, so we need global precipitation measurements. Extreme events, land surface modeling, looking at climate change and how extended record you can see variability in precipitation, and even world health. So if we go to the next slide, just a bit of a summary, but so the NASA Goddard Space Flight Center is building the GPM core satellite. That's a picture of it on the right. The instruments were provided by Ball Aerospace in Colorado, as well as JAXA, the Japan Aerospace Exploration Agency, who built the 2 radars. Now, everything has been integrated onto the core spacecraft at Goddard, and it has gone through a large array of tests. It's a completely assembled satellite now. I just saw the solar array deployment testing, and it was very cool. It's going to be shipped from Goddard in Greenbelt, Maryland, to Japan in the probably early November, late October timeframe, and it will be launched on an H-2A rocket in early 2014 by the Japanese, by JAXA. Now with that, I think I might have one more. So with that, I'm going to turn it back over to all of the other great presentations to talk about our ground validation effort, our education resources, and our partnership with the Iowa Flood Center. So I will take questions at the end with everybody else.
Great, thank you, Dahlia. Next, I am going to introduce you to Dr. Walt Peterson. Dr. Peterson is the NASA GPM Ground Validation Science Manager and the branch chief for the NASA Goddard Space Flight Center Earth Sciences Office of Field Support located at Wallops Flight Facility in Virginia. He served as an aerographer's mate in the U.S. Navy, a meteorological technician supporting the NWS and FAA. He received his bachelor's in mathematics from Southern Utah University and his master's and PhD right here where I'm located at the Atmospheric Science Department of Colorado State University. His interests are in cloud physics, precipitation processes, and radar meteorology. Dr. Peterson's office at Wallops oversees the NASA NPOL and D3R radars and the GPM ground validation disdrometer and rain gauge facility. That is quite a mouthful. Dr. Peterson, how are you today?
Oh, there I'm on. Hey, thanks a lot. Yeah, I'm good.
Great, great. And now today you are actually,
everybody.
yeah, you are not actually at the Wallops facility today. Tell us where you are.
No, actually, I'm actually out here in Iowa, a little bit to the southwest of Waterloo, Iowa, sitting in the NPOL radar container. I'm serving two jobs here this go around. I'm both sort of the mission scientist, but also the radar scientist for NPOL, working shifts. So I'm here today for 12 hours, waiting for something interesting to happen. We don't have a whole lot going on right now, but but I'm here nonetheless.
Great. Well, thanks a lot, and just go ahead and dictate to me when you need the next slide, and we'll go from there.
Okay, we'll do it. That's great. Okay, so Dahlia talked a great deal about GPM and the measurements that we'll make there. And one aspect of the program is ground validation, or GV as we call it. And here the idea really is pretty simple. And the idea is that we connect what we think is truth at the ground to what we're seeing in space. That's a pretty straightforward concept if you think about validation. And we have three basic approaches that we're doing this with. The first is pretty intuitive. Actually, probably most of you would figure it out, and that is, hey, we'll just sort of make direct comparisons between what we measure on the surface of the Earth using rain gauges and radar and such, and actually compare those measurements to what the satellite gets. So that's what we call, that's what we call a direct comparison. And then, that's not really good enough, because the problem that comes in there is, oh, well, what happens if you're wrong? Which actually, we are often wrong from space, and it's if you don't know why you're wrong, you have no opportunity to improve. So we really want to improve the methods that we use to retrieve precipitation from spaceborne remote sensing. So that gets us into the second aspect of validation, which is physical process validation. And there, what we're trying to do is actually study precipitation processes, the physics involved in precipitation, and how it interacts with the measurements that we make from space. For example, if we're using a radar, we want to know how microwave radiation interacts with individual precipitation particles to give us the signal we see in space. Whether that precipitation be rain or snow or hail, we need to know how the upwelling microwave radiation is interacting with that precipitation, because that's what we see in space. So we do a lot of physical process studies, especially in the pre-launch phase of GPM, and that's to sort of test assumptions we make in our algorithms, and also to come up with new ways of representing the physics of the precipitation in the algorithms in the context of what it is we think we will be seeing from space. Okay, so having done that, now we get down to this last part, which is really an end-to-end evaluation of the products, and it's called integrated validation, integrated hydrometeorology. And really, out here in Iowa, this is our real first stab at doing this particular kind of validation. And again, in an end-to-end sense, we're going to say, all right, we already have some satellites that are passing over the top, and they're making measurements of something that we think is involved with the rainfall process, and then we'll estimate a rainfall. Okay, so how accurate is that measurement? All right, well, we'll make an assessment of that using our ground instruments, and then you can ask the next question. It's like, okay, well, once you know how accurate you are and you know the uncertainties in your measurements, and you take all of that information and you plug it into, say you plug it into a hydrologic model for flood prediction. What are the implications for your prediction if you're off by, say, 10%? Or what if you're off by 20%? What if you're off by 50%? Or what if you think you're not off by much, but it could be plus or minus 20%? What are the implications when you put that estimate into a hydrologic model with its uncertainties? How bad might your forecast be for telling some population area, hey, you better watch out, you've got some flooding coming? So those are the three aspects of validation that we're tackling. You might ask the question, well, why don't you just use rain gauges and be done with it? And that's it's a fair question, it's a good question, and the fact of the matter is, we are actually using rain gauges. I mean, we would be kind of silly not to, right? Rain gauges have long been considered a gold standard for doing this kind of work. But rain gauges, as many of you probably know, are really not infallible. They're subject to errors. One thing that we do at Wallop's Flight Facility, and actually in all of our field campaigns, is a lot of work on quantifying or describing what our measurement errors for rain gauges due to things like this. In this example, wind flow. Here for example, we've got two pit gauges, which we call a reference, because they're not going to be impacted by the wind. This is actually the rainfall that you would measure at the ground, and we consider those to be a reference. And we'll put those next to some tipping and bucket rain gauges that you probably recognize, and that's kind of a common type of measurement that's done for rainfall, and you'll notice the anemometer there kind of in the middle for measuring the wind. This was just one example of kind of an extreme example of some measurements we made during Hurricane Sandy. Now, of course, that really is an extreme example for wind impacting a measurement, but if you look over on that plot on the right side, in the lower right, basically what happened there was as the wind speed began to increase up to around 30 miles an hour, we really started to see differences in the measurements. Now, 30 miles an hour, that's a stiff wind, but that's actually a fairly common wind in lots of storm systems, not just hurricanes. There we started to see big differences in what the response was between the different gauge measurement types. Some of those gauges are actually fairly advanced, what we call optical rain gauges. They're not tipping buckets, they're using optical signals to measure the rainfall. But in the end, what we saw was that between our sort of common rain gauges, and notice we had 3 of them out there, they all measured about the same thing. There was about an 11 or 12% error between those measurements and the reference measurement made by the pit gauge. And that's actually, in my mind, I thought that was pretty good for having the kind of winds that we have with Hurricane Sandy. But fairly typically we see that once the winds get above about roughly 10, 15 miles an hour, you start to see an error on the order of about 5% between the pit gauges and common gauges mounted as they are. And that error will increase the higher the gauges mounted above the surface of the earth. So aside from the obvious things with rain gauges like leaves getting stuck in them, or birds deciding to use them as a restroom or build their nest in them, which actually happens quite often. In fact, we've got a huge network down to the south of Wallops that we run, where we have to go out there about once every 2 weeks and clean the gauges out. It's just a problem. So you really have to be careful when you use the rain gauges for ground validation. That's kind of the point here, and we try to be careful about that. Okay, so maybe the next slide.
Walt, your microphone is cutting in and out just a little bit. I'm not sure if it's just your connection or what, but try to speak a little bit more clear into the microphone, please. Thanks.
I'll do it. Okay. So this next slide basically goes to another common error that we have when we just use single rain gauges located sparsely. This goes to the error of spatial sampling of rainfall. As we all know, rainfall can be pretty variable. And this, I call this the G, it poured on my neighbor's yard but not a drop on my lawn syndrome. And I actually used to live in Colorado, as Noah mentioned. And, this used to really chafe me at times because my lawn would be turning brown while somebody else's was green. And I didn't really care for that too much. But anyway, the issue here is just the spatial variability of rainfall. So a fundamental question that we can ask here is, how many rain gauges do you really need to make an accurate estimate of just the daily rainfall on the scale of a satellite footprint? So for GPM, this is on the order of 5 to 25 kilometers or so, a square on side. And so we use our network that's located south of Wallops. We've got about 25 dual rain gauge platforms. So these are individual platforms with 2 rain gauges mounted on them. The redundancy helps us to be sure that we're getting an accurate measurement of the rainfall, that one of our gauges isn't bad, for example, it doesn't have leaves in it or something like that. So all in all, we've got about 50 gauges in this little 5 by 5 kilometer grid. And this was just an example from one event in May of this year. Well, actually, that should be May of last year. But this was a daily rain accumulation, and one would think that on a daily time scale, you might have a fairly uniform distribution of rainfall over such a small grid. But in fact, in this instance, we had greater than 350% differences across this very small patch of area. And the issue here is that has significant implications for rain estimation and validation of satellite products, because there are, as you can imagine, it's rain gauges are kind of sparsely located across the world. And I know a favorite statistic that Dahlia likes to use is if you kind of collect all of the rain gauges that exist out there in the world and put them all into one area, it would be roughly a couple of basketball courts worth of area that you would cover, which is kind of an amazing statistic when you think about it. And so you simply can't put out enough rain gauges to make the measurement. And this is an example of where you have to be very careful. For example, picking one rain gauge out of there, you could be off by a couple 100% and never know. you would just never know. And right now, a lot of the satellite products actually blend rain gauge data with the satellite estimate. Even radar data, they use rain gauges to blend. And the problem is if you blend one gauge that's off by 200% because the rainfall varied that much, you're going to be way off in your rainfall estimate. You actually bias your estimate from space. So that's kind of some things we do with looking at rain gauges and direct validation. I guess we can go to the next slide. Thank you. All right, so we can make these direct comparisons. We can study how accurate we are doing the direct comparisons. And then, then there's this issue of, well, you've made the measurement and you've shown that the satellite is right, or maybe it's just wrong, but you better have a pretty good idea why you're wrong. It's just not good enough to tell an algorithm developer that he's wrong. They get a little irritated with you if you tell them they're wrong and you don't tell them why. So that's getting the physics right. Okay, so this is where the GPM field campaigns like iFloods come in. And here I've got an example of what we've got to do both in warm season with rain and also cold season. Again, the idea is to use all of the instrumentation we have, radars and gauges and astrometers, combine all that information at the surface, build a picture, if you will, of the cloud that produces the precipitation, understand how much precipitation fell, relate that in turn to, for example, what an aircraft might measure that's simulating the instruments carried on the satellite, and really understand the process from top to bottom. The key here is that GPM has got to produce accurate precip estimates over a really broad range of warm and cold season climates. It's going to the satellite itself will orbit from plus or minus 65 degrees latitude in the north and south hemisphere. So, so we're going to be sampling snow and mixtures of rain and ice and rain and tropical rain. We've got to be able to do all that well. So we do our field campaigns on the this. So we do those to test and improve our algorithms. And there's some examples of some of the places that we've been. The LPVEX, it's a light precipitation and validation experiment. We actually went to Helsinki, Finland. This is in late 2010 to look at cool season light rain in a marine climate. MC3E, that was a mid-latitude continental convective clouds experiment. We did that in Oklahoma. That was in 2011 to look at warm season convective rainfall over a land surface. And land surfaces are a little more difficult for us to deal with when we're using radiometers, which Steve will talk about in just a minute, and he'll kind of tell you why. We did a winter experiment up in Canada called TCPEX. That was for snowfall. And then, of course, we're doing iFloods right now here in Iowa. And then the last thing there is our setup along the Delmarva Peninsula, the eastern shore of Virginia and Maryland on the mid-Atlantic coast. And you'll see in those images, you'll see radars, you see, in some of them you see airplanes. We do use the NASA ER-2, which is a high-altitude aircraft that flies up in the stratosphere. It carries instruments that simulate what we have or will have on the GPM core satellite, and also the NASA DC-8. Same kind of idea. You use that satellite simulator to collect measurements that you think you might, that are similar to what you'll see from space, while you sample everything from the ground. And then we have an airplane that actually flies in the clouds, collecting information on the phytometeors and precipitation particles in the clouds. So that's kind of where we've been so far. Let's go to the next slide. So we get the iFloods, and I guess we can just go ahead and go to the next slide. So that's the Iowa flood studies. Okay, so this is the integrated validation of satellite estimated rainfall. I've got two plots here. In the upper right, that is a daily measurement of rainfall from, or actually a weekly measurement of rainfall from the 24th of May to the 31st of May this year. And actually the month of May in Iowa has been a booming month for rain. Roughly, in just May, roughly 8 to 10 inches in the domain we're sampling, which is way above normal for Iowa, and hence some of the flooding. But you can see in this week in that plot, you see the pattern of the rainfall that shows up on the Iowa flood information system that actually Ricardo was going to talk about. And then in the lower left, that's an equivalent spaceborne estimator for that same week from the NASA 3B42 product, also called multi-precipitation algorithm. And you see that there's some matches, some similarity there in the patterns in a gross sense, but actually there are some fairly significant differences in the scale of the precipitation features, where they occur, and really amounts. Okay, so questions then become for iFloods. Well, how accurate are these estimates? How accurate are the satellite products? And then, based on the measurements we make at the surface, can we actually improve those products, or at least can we get the surface products and satellite products to converge? To get closer. And then, how do we best use the products for flood prediction? Because there are these issues of satellite measurement making an estimate over say a 25 kilometer by 25 kilometer area. Where can you use such a large scale estimate for flood prediction? Does the basin scale have to be 1,000 square kilometers, 10,000 square kilometers, 100,000 square kilometers? Where can you use? How can you use the measurement best to do hydrologic studies and flood prediction? So that's what we're here for. Okay, next slide. So this slide is very busy, but all I wanted to do here was communicate basically that we've got quite an extensive network. And the reason that we came to Iowa actually was because this network exists here, because our colleagues at the University of Iowa and the Iowa Flood Center have such an extensive network of instrumentation and infrastructure that's already resident in Iowa, and they're actually experts at hydrology and flood prediction. And so we wanted to work with them, bring our equipment and work with them to really make some detailed measurements. And you'll see in the up there where it says Turkey, that's the Turkey Basin, and we deployed a dense network of rain gauge platforms up there. Also in the South Fork Basin, where we've got colleagues from the USDA and ARS have gauges in there. These are very dense networks of gauges that we added to. And then we're right in the middle is where the end-pole radar, that's the NASA end-pole radar, and D3R radars are located. So we've got two radars located right here to sort of co-stare, if you like, at precipitation volumes at 3 different frequencies. And again, Steve will talk a bit about that. And I guess we can go to the next slide. So this is an example of the dual platform rain gauges that we're using. So these dual gauges, basically, I mentioned the measurement consistency, which is very important. They transmit the data back via cell modems over the network, so we can see the data in real time. And they do provide a reference for the radars. So when we deploy these things in fairly tight networks, we can use them as a form of truth for the radar pulse volumes, which is good. That allows us to make sure that we're at least in the ballpark with our radar estimates. And then each one of these platforms actually has soil probes, 4 soil probes connected to them. I think they're situated at 5 centimeter and 10 centimeter depths. And what the soil probes allow us to do is measure soil moisture and temperature. So that connects sort of that rainfall infiltration and the potential for runoff to what we're measuring in the soils. So we've got those on all our gauge platforms too, and those are very important inputs for flood prediction models. Okay, next slide. Next slide. There you go. Thank you. So I mentioned precipitation particle measurements. This is an example also of sites that we have located away from the radars. 2D video astronomer. These basically image individual raindrops or snow or whatever it happens to be, and then count them and tell us about sizes, shapes, and things like that. That's very important for a radar estimate of precipitation. So we've got several of those distributed about. Micro-rain radars, these are vertically pointing radars that give us information on the low-level profile of the rain. Sometimes the radars have a tendency to overshoot the lowest levels of the troposphere, maybe the lowest kilometers, so you'd like to have a little bit more information there. And so the micro-rain radars give us that information. And then a parsable distrometer, which is essentially a laser distrometer. The instrument at the top there is a head that has a thin beam of laser light that the drops fall through, and each one of those drops then gets sized and counted. And so that's all very important information for our radar estimates, to truth what it is we're seeing with the radar. And the next slide. And then here's of course, my favorite part. I'm a radar guy, so what can I say? So here on the left are the end-pole radar, the NASA end-pole radar, and the D3R radars. And you'll see the end-pole radar is a very large radar. The dish on it is 28 feet. It's a 1 degree beam width, actually a little shy of 1 degree, a very tight beam. And it's a dual polarimetric radar, which means that we can image precipitation particles in both the horizontal and vertical axis of the drops themselves. It gives a whole lot of information on raindrop sizes and shapes and whether or not we're looking at hail or rain. The dual frequency radar, the D3R radar is a dual frequency radar. It looks at precipitation at 2 different frequencies, similar to what we're going to use in space. And so we reference the D3R radar with the end pole estimates. And actually, iFLUDS is the first experiment that we've co-located the radars like this and been able to collect just an amazing amount of great data. And so we'll really get a lot out of this experiment using those two radars. The radar on the right is actually one of 4 University of Iowa X-pole radars, and it's an X-band radar. It also scans similar to the V3R and the N-pole, and those are located in various areas in Iowa, 2 up in the Turkey River Basin, and then 2 down towards Iowa City. Okay, next slide. Okay, so we use these radars in a very specific ways. First thing that we do is pretty standard, and it's something that you see quite often on your TV news at night. They'll show you what we call a plan view or a horizontal view of the rain or the storms. And so we scan, I don't know if the movie will work here, Noah, you can try. Basically, the radar scans the horizontal plane. You see it just kind of scanning like that. And so we'll either scan in a full 360-degree circle, or we'll scan just using a sector, like we're doing right there. By sector scanning, we can actually scan only the parts of the region that have rain in them, which speeds up our ability to sample. Okay, next one. Let's see, so that's PPI scanning. So that's for rain mapping. Okay, so the next one is range height scanning. Okay, and all we're doing here is slicing and dicing the atmosphere, essentially. The idea here is to simply create vertical cross sections of the clouds and the precipitation. The idea here is then to study the physics of the precipitation, which is primarily controlled by what's going on in the vertical in terms of temperature and humidity in the clouds. So you're looking at ice and hail and gravel and snow, and then everything melting to become rain when you look at things in the vertical plane. And you see the radar scans up and down along with the V3R radar, and we kind of switch our azimuth angles every once in a while to catch a new part of the cloud. And we do that really rapidly, although it's a bit blocky in the video here, so that we can get a good view of the whole rainfall process. That's what allows us to connect the ground to what the satellite sees. Okay, next. So here's an example of a case we collected on May 20th, right here during iFLUDS. This is a severe storm event. Actually, on the left there, you see what you might see on any day on your TV weather news. TV weather. That's a squall line, a big leading line of intense convection and thunderstorms, followed by some more gentle stratiform, what we call stratiform rain. And we sampled this on the 20th. And this storm was followed by a couple others, and the result was a flood wave that occurred later in that week. And at the same time, we then mapped the rain and accumulated for the day on the right side. That's a map of the rainfall that we accumulated for that event. And actually, when we compared it, and this was without checking the data, without doing any real quality control on the data, what we found was that we had a fairly good match to our existing gauges and distrometers, and we're very encouraged by that. So we were within 10 to 20% of the other estimates. So this gives us confidence that we can accurately map the rain on kilometer scales out over a 10,000 square kilometer area, which is very important for inputs, creating a reference input for flood models. So we combine those ground and radar measurements to make the reference rainfall maps, and then we use those reference rainfall maps in turn to compare to the overpassing satellites, and then those estimates both get fed into a flood model, and you can start to assess what your uncertainties are in the satellite estimates, but also the ground estimates and the impacts on the flood forecast. Okay, thanks. Next slide. Okay, this was just an example from the Turkey River Basin. Up in the upper right is a plot of daily rain, again for the 20th of May. You can see the sort of the variability in the rainfall in the basin. It varied from about an inch, actually, to less than half an inch. And each one of those little plots there in sort of the matrix, if you like, of a time series of rainfall plots, each of those represent the output from the dual gauge platform. So you can see that the gauges performed very well, generally always agreeing to within 10%. And typically between rain gauges, you put them right next to each other, we look for less than 10% error between the two. So they did very well. I already mentioned how the rain varied, and again, these are a reference for both radar and satellite estimates. Okay, next slide. And then here's an example just from some of the distrometer data. This is from the 2D video distrometer. These are up in the upper panels. Those are images of large oblate raindrops. Rain, when it falls, typically starts to deform, start to resemble something like a football the larger that it gets. And that change in shape is very important for how we remotely sense the rain using a polarimetric radar, because as it becomes more horizontally oblate, or as it gets a larger horizontal axis than vertical axis, that's when we can really see the signal in the radar data. It tells us something about the size of the raindrops and hence the liquid water content. And then on the bottom there, those particles look a lot more spherical, a little bit irregular but more spherical. Well, there was some hail mixed in with the rain on this day, and so we imaged it here with the astronomers. This is just small hail. But again, there's a big difference between that spherical signature and that horizontal signature of raindrop. And you can see how we might be able to discriminate between hail and rain when we use a polarimetric radar, because we're seeing both horizontal and vertical return. So that's a reference for how we identify precipitation types and sizes with the radar. Okay, that's fine. And then just very quickly, an example of how we cut through the storms and what we can see. So on the left, this is a range height indicator, an elevation scan that shows you where we're cutting, slicing, and dicing the atmosphere. So you can imagine that the satellite is really measuring or looking at radiation that's upwelling from the Earth's surface, that anything that gets in the way of the between the ground and what the satellite sees is going to create a perturbation in that measured radiance. And that's what a storm does, and that's what the BlueSat does. And so we want to know how the precipitation is distributed in the vertical. And this shows an example of how we can identify the different precipitation types and the process that you're making rain in the vertical. So you've got graupel over there on the right side. You've got graupel and snow, which you can see way up in the storm. And then hail, there's actually a hail core in the storm. And we can see it fall through and actually melt. You become large raindrops. Those large raindrops are important because they can actually bias the signal that you get from a radar if you just use the return power. So you have to use something besides the return power to get a better estimate of the rainfall. And the polarimetric radar affords you that capability. And then, of course, the rain underneath. And so we can study the process. Here, the process to make the rain is really obvious. Snow is up in the upper regions of the cloud, and there's some cloud water up there, and it actually grinds up to become graupel. And graupel is kind of these soft, snow pellety looking things. And that grinds even more sometimes to become the hail, and or the rain even freezes to become hail. And it collects a lot of cloud water, and eventually it just gets too heavy to suspend in the cloud anymore. It falls out and it melts, and eventually you get raindrops. And the image there in the lower right-hand corner is actually what raindrops look like as they're falling as a function of their size. So you can see the larger the raindrop that you get. Oops, mine just. Oh, there we go. Okay, we got a weird. Okay, we had a weird error there. Anyway, you can see the larger that the raindrop gets, the more deformed it gets, which means the better we can see with the polarimetric radar. Okay. Was there another slide? Or was that the last one? Okay, there is one more.
This is the last
All
one
right.
here, yep.
Great, yeah. So just to wrap up, basically, this is just another example from the 20th. If you can start doing some preliminary comparisons. And so on the left, lower left there, you've got basically, if you just took the reporting rain gauges and you contoured them and you made a plot, that's as far as the gauges are concerned, that's what it looks like for that day for what rain fell. Okay, then you can say, all right, well, what did the satellite see? And you go over it, there's the satellite from the hydro estimator. You can say, well, that kind of looks something like what the gauges collected. But on the other hand, in the lower right part of that satellite plot, you actually see a big blob of heavy rain that doesn't show up in the gauges at all, right? So there's something not quite right there. And then you can go over to all the way to the right side where the radar estimator is, and you can see that really neither the gauge or the satellite estimate were really bang on. There you really wanted to make the measurement with the radar, and it turns out that the radar gave us a pretty good comparison to our gauge platform. So the question for IFLUS is, okay, so how do we improve these estimates, and how do we best use the information? And that's what our measurements are going to tell us from this field campaign, and I believe that's all I've got.
Great. Thank you so much, Walt. That is fantastic. We are going to move on to the next speaker here, Steve Nesbitt. Steve is a professor of atmospheric sciences at the University of Illinois and a mission scientist on the GPM ground validation field campaigns. I'll also mention that he, too, was a graduate student at Colorado State University, where I am now. Steve uses the data collected to improve the representation of cloud microphysical processes using radars, aircraft probes, and surface instrumentation in satellite precipitation algorithms to improve global precipitation estimates. Again, quite a mouthful. Steve, how are you doing today?
I'm doing fine. Thanks a lot.
Great.
Yeah.
Let
I
me
just want to make a minor correction. My professor, my major professor at the University of Utah would be a little offended if he knew that I was, associated with Colorado State. But I did work at Colorado State for 3 years. But anyway.
Thank you for the correction. Sorry about that. Yeah.
But anyway, yeah, thanks a lot for having me. Today I'm going to talk briefly on how we actually do precipitation measurement from space. I know Dahlia and Walt touched on a lot of the ideas about how we actually do this, but my goal here is to actually hopefully give you some insight into how we use physics to actually do the precipitation estimate from space. And as you'll find out, it's actually a very interesting and evolving research topic because we're finding that there's a lot of challenge to this that is going to challenge us going forward over the next decade or so to actually make high-quality estimates globally from these satellites. So if we go to the next slide, we'll just talk about some basics. And the primary thing that we're doing here is, you would call, in the meteorology community, you would call this remote sensing. And we're trying to get information about something that we're interested in without actually touching or taking measurements within that particular medium. And some other examples, of course, from nature. We're not the first ones to do this. Obviously, in nature, things like bats and dolphins use sounds to find out information about food that they're interested in. Of course, we've adapted that to submarines to actually use sonar to find the ground, hopefully that they don't interrupt or intercept the ground. So they've used that technology, obviously, in biological sciences to be able to find animals. And if you go fishing, you can use a cheap version of sonar to find fish underwater. But in the field of remote sensing, we use light primarily to find information about objects. And an example that you've probably experienced, hopefully not too many times in your life, is obviously an X-ray. And that's where you're using light in the form of X-rays to image what's inside of your hand. Same thing goes for MRI, which is actually closer to what we use for radar in terms of the electromagnetic energy that we use. And then, of course, astronomers use remote sensing to find about our galaxies that surround our planet. And we've launched satellites to be able to do that, including the Chandra X-ray Observatory. So going on to the next slide, it's a pretty broad field, and people have used remote sensing to learn a lot about our planet. And why would we use remote sensing for precipitation? Well, first of all, all you CoCoRaHS members out there, we've got a lot of gauges in the U.S., and you all work tirelessly to collect those measurements every morning. And myself, I'm a CoCoRaHS observer, and I know how that is. But as Walt has talked about, your gauges only really cover a very small region of the planet. And as you can see on the map down below, even with all the rain gauge observations we can take across the planet, we obviously don't see much over the oceans for obvious reasons. We don't see much at high latitudes like Antarctica or Greenland, and also in many tropical regions over land, we just don't have a lot of observations. And so we want to learn about precipitation, its role in the climate system, its role in society. We have to develop these remote sensing techniques to be able to learn about precipitation's role in climate and society. So going forward, we need to develop the apparatus to be able to make these sorts of measurements. And the way we do that is we exploit various parts of what we call the electromagnetic spectrum, which is just a fancy way of describing light or radiation, you may have heard. So when we talk about radiation, we're talking about a broad range of waves that exist, and of course the most common one to humans is the visible spectrum, where you can see that little rainbow down in the bottom. And when we're talking about visible light, we're talking about a small portion of the electromagnetic spectrum. You may have learned in your physics courses that there are spectra of light that exist well outside of that visible spectrum. Our eyes are only sensitive to a small part of that. But as we go to the high energy part on the right, we're talking about ultraviolet light, X-rays, which can penetrate, of course, the human body, and gamma rays, which penetrate everything, are very dangerous. But as we go to the other side of the spectrum, we go towards what we call infrared radiation, which is very similar to heat. So if you go near a campfire and you feel that heat, you're feeling the infrared radiation. Infrared radiation comes off of our planet, and we can use that information to actually tell the temperature of things on the planet, like the surface, clouds, and other things in our atmosphere. And I'll talk about how we use that to sense precipitation in clouds. And as we go further towards the lower energy of the spectrum, we get into what we call the radio spectrum, or microwaves. Okay? Now, we use microwaves in our kitchen to heat water and cook our food. And the fact that if we bombard our food with that radiation and it heats up, it tells us that radiation is actually interacting with the particles in the food and causing the temperature to increase. So that tells you that water, one thing that obviously is involved in precipitation, is sensitive to that interactions in those sorts of wavelengths. And we can exploit that to tell about where water vapor and liquid water is in our atmosphere. And we use that with the radars that Walt has talked about. We specify specific frequencies also because we want, as you see along the top, we want to make sure that we can sense radiation that actually can go through the atmosphere. There are certain frequencies that are strongly absorbed by the atmosphere. Those happen to be especially in the infrared. But outside of that, in the microwave and in the visible, we can actually use that, and part of the infrared spectrum, we can have that radiation pass through the atmosphere and sense that from the top. You can see it from satellites. So going forward, in the next slide, we can see that there are different types of remote sensing that we can do. And just as a real down-to-earth example, I've got two examples here. The first one is something that we all do with our cameras. We take photographs. And we can mount cameras on satellites to take pictures of the Earth. We can set those cameras up to be at different frequencies in the electromagnetic spectrum, and then we can use that information that we get back to interpret different things about the Earth and the atmosphere. Contrast that with a picture of a similar area taken by what we call an active remote sensor. Okay? On the top, a camera is what we call a passive remote sensor. Basically, take any information that comes to the camera, we record that, and then we try to interpret that image. We can tell certain things about the image, like the color. We can even, if we're in the infrared spectrum, we can tell how hot or cold something is. But if we use an active remote sensor, which by definition is where we actually transmit information in the form of electromagnetic radiation, that electromagnetic radiation interacts with something like the surface or a cloud, and is somehow changed by it, primarily scattered back towards our sensor. We record that information, and we see what the amplitude of that signal that comes back. We can tell how long it took to get to the object and come back, and that can tell us how far away it is because the speed of light is constant. We can look at how the wave was changed, look at different properties like the amplitude, what we call the polarization can change, and et cetera. And we can use that information to kind of back out some properties. And in this case, this image was actually taken by what we call a LiDAR, or a light detection and ranging instrument, where we could actually measure the topography of the area around Lake Tahoe and use that information to estimate how high the surface is above sea level. So in precipitation, we're going to use similar techniques. If we go on to the next slide, we can talk about how we use some of this information. So we actually do use sound in meteorology, and on the left I've described a couple different ways we do that. One is that we actually use sound to measure the sizes of raindrops, and although this technology we don't use, we can actually use distrometers that measure the sound waves that come off of raindrops when they hit a little membrane or the sea surface to measure how large they are. We can also transmit sound up into the atmosphere and use a SODAR, it's called, sound detection and ranging, to measure temperature and humidity profiles in the lower atmosphere. But for precipitation, in the atmosphere, we mainly use electromagnetic waves. And in passive sensing, we can use various parts of the electromagnetic spectrum, including visible imaging. The second one should say infrared imaging, and then the third one is microwave imaging, different frequency bands. And then we also use active to use what we call LIDARs, which are light detection and ranging, which are typically in the near ultraviolet or visible or infrared. And then lastly, we use radar, which is radio detection and ranging, where we use the microwave spectrum to send pulses of energy out, and we measure how long it takes for those waves to come back. We measure the frequency shift, kind of like a passing train, how that sound changes with time as the train passes you to tell how fast the particles in the atmosphere are moving relative to the radar. We also, as Walt mentioned, look at the polarization shift, which also tells us about the properties of those particles. And on the left, you kind of see a montage of different types of images that we have. So on the next slide, I'll show you an example of precipitation remote sensing from satellite. And let's just skip this slide, and we'll talk about this example that we have here. So here, we've got an example of a hurricane, which is off the coast of South America. And we're looking here at 4 different frequency bands of the same scene. Okay, so on the top left, we've got an image from the infrared part of the spectrum, which is at about 11 micrometers wavelength. So this is very close to the visible, but not quite. It's a little bit longer wavelength. Contrast that with the image from the same time on the upper right, which is from the visible part of the spectrum at about 0.6 micrometers. So that's right in the green band that you would see from your eye. So if you're on the satellite, took a picture from about 400 kilometers up or higher, that's what you would see. So you can see that there's some correspondence between what you see in the infrared. The infrared is primarily just a heat signature. So the cold clouds are actually, that are higher in the atmosphere, are radiating at lower amounts of energy, and so that they appear white on this image. Where you have darker images, that's where it's warmer. You can see almost down to the land surface. But on the right, you see some confirmation of that, although there's some differences. Okay. Now, if we move into longer wavelengths, into the microwave, on the bottom panels, you see 2 different frequency bands in the microwave. And it turns out that these are sensitive to either the emission of energy in these wavelengths from precipitation in the atmosphere primarily, or the land surface, or the scattering of microwave energy out of that path by hydrometeors in the atmosphere. So warm energy comes up from the surface, and that gets scattered out of your field of view and makes it look cold from the satellite's perspective. It turns out that the images on the bottom are much more correspondent to where the precipitation is actually happening compared to the images on the top. And so it has the advantage of being able to map the precipitation much more closely, although it's not perfect, as Walt showed you before. So if we go on to the next slide, we can talk about our first question. So what electromagnetic frequencies will GPM be using to measure precipitation? So this is a little bit of a review. And you can switch over to the question.
All right, interactive time. You have your choice with a hint that more than one may be correct. You should be able to choose more than one here. We'll give you about 5 more seconds. And we'll go ahead and close it and share the results here.
All right, very good. So yeah, we're going to be using infrared and microwave. So it looks like, I don't know if it allowed people to pick more than one, but everybody's on the right track pretty much. So going forward, so visible and infrared images are actually very easy to take, and we've been measuring these for almost 50 years from space. And these are primarily done by what we call geostationary satellites. And these satellites are launched by the U.S. and other nations, including Europe and in Asia, which are able to take pictures continuously from this geostationary orbit. The special thing about this orbit, which is about 22,000 miles above the surface, is that these satellites can sit in the same place and take pictures, as frequently as every minute. And so we can map where the clouds are very reliably. As we go forward, we see how we take this information and change it into precipitation. It's actually quite simple. It states that as the colder the clouds are, the more likely they are to be deep enough to produce precipitation. And statistically, we can show that there's a relationship. And so on the next slide, it shows you that relationship. So basically on that map on the upper left, the colder the clouds are in terms of Kelvin, the more likely it is to produce precipitation. And statistically, that relationship has been derived. But on the upper right, you can see a comparison between a radar measurement on the left, an A, and a cloud top measurement from satellites on the right. And you can see that while they're close, they're not generally that correspondent. So if we're really trying to nail down what the rainfall rate is at a particular time and space location, this is not maybe the best way to do it. And that's why we have GPM. So in GPM and other constellation satellites, on the next slide, we'll see that we have a lot of satellites up there. Obviously, this looks like a picture out of the movie WALL-E, if you've ever seen that, with all the space junk. But there's a lot of satellites in what we call low Earth orbit. And these orbits that are lower can take advantage of the fact that they're much closer to the surface to be able to measure the microwave energy coming off the clouds, both active and passively through the sensors. And these orbits are around 300 or 600 miles above the Earth. And just to give you an idea, this is the same altitude as the International Space Station. And here's a picture showing what you'd see from that platform. And you can see we're much closer to the clouds, and we're able to use the microwave sensors to profile through the clouds. So going forward into the next slide, you can see the constellation of microwave satellites that are up there and will be up there in the next few years. Okay, so you can see that there's several satellites that have these passive microwave sensors out there that are launched by both American partners like NASA and NOAA. And then the one I want to focus your attention on is the one in the upper right, which is the GPM Core Observatory. And that's the one NASA will be launching next year. It will have both an active and the passive sensor on it. So going forward into the next slide, next quiz question, okay? So why aren't all satellites in geostationary orbit where we can continuously monitor our hemisphere? So I mentioned that geostationary satellites can take a picture every minute, but it turns out that doesn't work so well.
All right, we've launched the poll. We'll give everyone 10 or 15 seconds here to choose their best answer. Looking good. About 5 more seconds. Great. I'll close and share the results.
All right, so we had a few people enjoying my joke on the last one. Obviously, budgetary issues may be a problem, but the real issue is that the sensors can really only collect data when they're close to the Earth. All right, so let me talk a little bit how we actually take this information and combine it into products. Okay, so obviously this is a complicated process that scientists and engineers have worked a long time on. We continue to improve, but what we're doing is we're taking what we call brightness temperatures that the satellite measures. Okay, and in the passive sense, that's all we have. We have brightness temperatures that are at different frequencies in the electromagnetic spectrum, and we need to take that information and kind of put it in this big funnel. And even to a lot of scientists, the actual methodology that goes into these retrievals is a little bit of a black box. It's pretty complicated. But what they do is they take this information, which are the observed brightness temperatures, and they compare that with a database of simulations and observations that have been collected prior, and they do a statistical model to try to match those two up to the best that they can. Okay, and so it's those three components that take kind of the observations this database, which is based on our physical understanding of precipitation in the atmosphere, how that interacts with the electromagnetic radiation in the atmosphere, also the surface, because that's also seen by the satellite. And all that information is combined to, in a statistical way, to come up with an optimal answer for how much precipitation is actually coming out at the surface. Okay, so there's a lot of steps here, and it's complicated. Now, these retrievals, which are based on the passive imagery, basically just camera images in different frequencies, are good because they're better at finding the precipitation area, as I showed you, than the infrared images, which are just basically heat maps. However, there's those three parts that I talked about have to be all well and good and very representative of the actual physics going on. And as we're finding with our validation campaigns, there's still work to do, especially in high latitudes and snowfall, where the surface actually plays an important role in electromagnetic energy. And also in high latitude oceans where there may be ice cover. Those are challenges. But the good thing is that we get these passive microwave estimates that are higher quality than infrared, and they come every 2 to 4 hours. And so we actually get a fairly high temporal scale on these estimates. Now going forward, I also talked about our active satellite radar retrievals. Okay, and this is where there's actually a radar mounted on the satellite that points straight down and scans back and forth under the satellite and provides us a nice curtain of images that can actually map the precipitation as a function of height. Okay, what I'm showing there on the right are some simulations from an aircraft-mounted radar that's very similar to what will be mounted on the satellite next year. And from this information, we can tell the difference between the types of particles in the atmosphere, for example, rain versus snow. We can look at the intensity of the echo that we get back, which can tell us about the size of the drops. The satellite will actually have 2 different frequencies on it, which is an improvement over past satellite rainfall radars. That will give us information about the sizes and the types of particles that are in the atmosphere. And based on that, we'll actually be able to provide quite high quality rainfall estimates from the satellite platform. That's very similar to what you get from a ground-based sensor. Okay. Now the big caveat or the problem here is that there's only one of these on one satellite. So we won't be able to map precipitation with any sort of temporal resolution with this sensor. So we'll have to use this sensor in a mode where we train the passive microwave information because all these satellites are going to cross each other. We also have the core satellite passive sensor, which will be able to compare directly at all times with this radar. And so that we'll be able to train the passive sensor to be as accurate as we can, and so that we can use that as a kind of spaceborne validation reference for all the other sensors that are up there. And so the radar is actually going to be a critical point of information. And that's why we're spending all this information with validating it with all this time. So my last question here, why are satellite-based radars usually more accurate than passive infrared or microwave estimates of the intensity of rain or snow at any given time? So look at that one.
We have launched the poll. Everyone is voting. We'll give you about 5 more seconds. All right, and we'll go ahead and close and share the results.
All right, so it's like the large majority said radar has a lot of advantages. We just wish that we could afford to launch many, many of them so that we could have lots of high-quality information. But the passive is also a valuable tool that we'll be able to use. Okay, so the last step, and this will really wrap up my presentation, is that we take all this information from all these satellites, which gives you overpass coverage every 2 or 4 hours or so. We have to combine that information with what we have on the ground, including gauges and infrared estimates from geostationary satellites, into uniform products that users can use, like people trying to predict floods. And so there's actually a group of people that actually are experts in combining all this information to provide what we call these 3-hourly operational products. And for GPM, we'll have these products that will update every 3 hours, and we'll have about 25-kilometer resolution, so about the size of the city or town or a county or so globally that will be able to have these sorts of estimates. And with GPM, these will be very high quality, and we're hopeful that a lot of users from weather prediction, climate understanding, to applications like hydrology and societal impacts will be able to use these products. So that wraps it up for me, and look forward to any questions at the end. Thanks a lot.
Great. Thank you very much, Steve. So we're going to start getting towards the end of the webinar here. We've got two more speakers, but both of them are shorter in what's going on here. But next we are in for a treat. We're going to get a brief overview of a very cool web tool that is free and open to the public. So let me introduce you to Ricardo Mantilla. Ricardo began working at IIHR, which is the University of Iowa's Hydroscience and Engineering, just a few months before eastern Iowa's historic floods in 2008. At the Iowa Flood Center, Ricardo is currently working with his team to develop models to help predict and forecast the timing and magnitude of flood events. So Ricardo, I'm going to go ahead and make you the presenter, and you can go ahead and accept that.
All right, excellent.
And we should be able to see your screen. Yes, we can see the Iowa Flood Center.
Thank you, Noah. Can you hear me well?
We can.
Okay, excellent. So thank you for the opportunity, and we have been hearing quite a bit of information about these new, pretty amazing rainfall products that are going to become available, and that are available. And one key question for us at the Iowa Flood Center is, how do we make this information available and useful to people? And we know there is a wide range of expertise out there. And when I say useful information, we have a particular interest on how this information relates to potential for floods. And the Iowa Flood Center has created a prototype platform, online platform that we call the Iowa Flood Information System, that I'm going to present here, give a live demo, and hopefully everything's going to go smooth. The Iowa Flood Center information system can be accessed by going to the iowafloodcenter.org website and clicking on the Launch IFIS button here. So that will take you to the main window of the Iowa Flood Information System, and you can get a little bit of a tutorial down here on how the system works. So hopefully I will entice you to visit our website once the broadcast is finished. I'm going to start by showing you a little bit of the information that we are presenting here, and I'm going to start with what we call the state overview of the information. And when you hit launch on the website, the first thing you're going to see is a map of Iowa and some of the gauges that are currently reporting some level of flooding in Iowa. So as you can see, last week this map was very illuminated, but now the conditions are improving a lot. So we're seeing less flooding. But these are all the places where we are monitoring stages, river stage, and that have some flooding. Now, with that being said, here you can access the information of all the other places where we are collecting information. And this information includes stream flow measured by the USGS. So these yellow dots are stations run by either the USGS, the Army Corps of Engineers, or any other entity that reports information to the National Weather Service. And the green dots are information that we are collecting using our own network of instruments. One thing that it's interesting here that you can access is that now you can see the rainfall that's been falling over Iowa in the last 15 days. So you can use the tools in the website to check at the values of rainfall information on the previous day. So here I'm going back in time, looking at June 8, June 7, the rainfall that we have had in the last few days, which fortunately, we have been getting a little bit of a break on the heavy precipitation that we saw in the last few weeks. But with that being said, another tool that we have is this option to look at the cumulative precipitation over the last 15 days. And just as I was looking at the daily rainfall, now what I'm looking at is the information of this accumulated rainfall. And as you can see, as I go back in time further, in the last 2 weeks, we have a few regions in Iowa that have been receiving quite a bit of precipitation. And whenever we look, we see red on these maps, we know that conditions are primed for flooding if new precipitation, new intense precipitation comes in. Now, one of the most important features of IFIS is the idea of serving communities specifically. And in Iowa, there are about a little bit over 1,000 communities that are located close to rivers. And we want to provide forecast or some information for all of these individual communities. And this is when the specifics of IFIS come in, because then you can go, and if you're particularly interested in a specific city, you can go on the website and then look for the city of interest. I'm going to choose Cedar Rapids because of maybe it's a large city, and the historical floods of 2008 and floods this year have been affecting. So once you select a particular community, the system will show you the watershed that drains that particular community. So then information becomes more relevant to you, because if you want to look at the cumulative rainfall of the last, again, 8 days, you can determine whether that rainfall will be flowing through your basin at one point or another. And then you can look at the rainfall patterns of the last few days and then see whether that rainfall really affected the basin that drains through the drains that your community is draining. So then information becomes more specific and more relevant for the community itself. This is both in terms of rainfall and also in terms of the information that is being collected upstream. So that way, if you receive a forecast from the National Weather Service that you have a floodway coming and that you are going to see this rainfall flowing through your community, then what you can do is look at the information that is being collected upstream and see what is happening there. So you can see the information that was collected in the last 15 days, and you see maybe a wave that was there a few days before. Then maybe you can see how the water is propagating through the system. So now, of course, the system is set up to present the forecast that in some locations the National Weather Service provides, but there are a number of locations where the National Weather Service does not provide a forecast. And in those places we are beginning to fill the gap with the models that we're developing. So now we have a complementary system. We're trying to complement the forecast that the National Weather Service is providing. And one question that is very, very important is, what does all this mean? So when the National Weather Service or us tell you that the river might be hitting, say, almost 20 feet of a stage, what does that mean for you and your community? Well, the Iowa Flood Center has also been developing inundation maps, and I'm going to go now to a more local view of Cedar Rapids. Now, when you get information of this kind saying, okay, maybe in the next days, you're going to be observing a stage of 23 feet in Cedar Rapids. What does that mean for you? Well, now you have maps that have been developed specific for communities, specifically for some of the most important communities or more populated communities in Iowa. And in there you can navigate and then see for yourself whether your property, wherever you are interested in, will be inundated. So these tools provide a real hands-on opportunity for different levels of expertise to access the information that we are providing, and more importantly, to interpret the forecasting that we're doing. As Walt said, and throughout the other presentations, none of the forecast and none of the rainfall information comes without uncertainty. And we're trying to create a platform that is able to communicate this information in real time so that as the precipitation evolves, then the public can be informed very quickly about how the conditions in terms of flooding change. And I think with that, I'm going to stop, and hopefully, as I said, you can visit the website. Just go to the Iowa Flood Center website and click in IFIS and send us your feedback. No, thank you.
Great. Thank you, Ricardo. And I know Ricardo's got to run off to another meeting, so I don't believe he'll be able to take any questions after this. But I personally encourage everyone to go, and even if you don't live in Iowa, it's just such a neat tool. It's really neat to play around, and I really recommend watching the tutorial to help you get started. For me personally, I just can't wait till a program like that opens up nationwide, so it's not just for Iowa. We're going to move on to our very last speaker, who is going to also be quite brief, Dorian Janney. And as I make you the presenter, Dorian, let me just introduce you. Dorian is the education specialist for the GPM mission. She taught for 33 years at the grade levels and finished, at all grade levels, and finished up her career teaching middle and high school science classes for the last 15 years. Dorian achieved her National Board Professional Teaching Certification in early adolescence in science. So, Dorian, are you there? And Dorian, you need to unmute yourself here, maybe, I believe. And I can see your screen. And Dorian, let me see if... Oh.
All right, can you hear me now?
Perfect. Thank you so much.
All right. You're so welcome. Well, good evening, and I really am going to be keeping this brief. It is just amazing to hear all of this information, and for me as a translator, which educators are, trying to find ways to take this information and make it more understandable to the public, and particularly to students. As you can tell with the complexity of the information, it's a pretty challenging thing to take on. But basically what I wanted to do is to show that right now there's a huge emphasis on STEM, which is basically science, technology, engineering, and mathematics. And I would say that if people were to look at our website and look at the amazing things that we have to offer that explain how we are able to integrate science, which creates the need to know. So, for example, how much precipitation is falling across the globe. Technology, which allows us to make those measurements, just as Steve was explaining to us. Engineering, and there Walt gave a wonderful explanation of the engineering there. You know, and all of this is able to be accomplished through the use of mathematics. So it's just really important that we are showing students the real-world applications for these things. With the iFlood campaign, we have another really wonderful opportunity to now be looking even more closely. So how can we better predict flooding in an effort to assist people who are living in flood-prone regions? And so again, here I have broken that out into the science, the technology, the engineering, and the mathematics that would be able to be integrated in order to help people better understand that. And I just wanted to make you aware of two resources that we developed for the iFloods campaign. Here is one called Too Much, Too Little, and you can see this simply by going to the GPM Education website, which is right up here. And then if you go to GPM Originals, you'll be able to access all kinds of materials. Well, here is one, GPM, Too Much, Too Little, and this explains how we're able to make predictions about things like flooding and droughts, and then use that information to better assist, everybody with understanding the importance of that and how we're able to make predictions about it. Okay, then the other one we created specifically for this purpose is the iFloods iQuest. And that's something if you're a teacher, you might take a look at, and if you know people who are teachers, or if you're just interested in learning more about iFloods and real-world applications for that, please feel free to go to that website. Again, that's one of our original materials. So finally, I'm going to leave you with just giving you some more things to do in your spare time. Please visit our GPM educational website. Visit the CoCoRaHS website. Just wonderful materials there. And if you want to put in a rain gauge at a school site, there are all the instructions that you need to do that. And we are also accepting GPM Master Teacher applications through June 15th. So if you're a teacher who thinks that you might like to take some of these real-world applications and get students engaged and excited about science, technology, engineering, and mathematics, we hope you'll consider joining us. So thank you so much, and thank you for hanging in there with us. This ended up going a little longer than we anticipated, but it's really very timely content.
Great, thank you so much, Dorian, and I'll go ahead and take control back and just finish off the presentation here. I do have a couple of questions that have come in. I know we have gone over, so we understand if you have to get to dinner or whatnot, but I do have a couple of questions I'd like to field, and Joseph is asking, is the radar on the GPM core observatory, is the radar there dual pole on the GPM core?
Walt, I'll pin that.
Yeah.
It's dual frequency, actually.
Okay.
Not dual pole.
Thank you. And Joseph is also asking, what do we mean when we say extreme rainfall events, quote unquote extreme? What is there a threshold that makes an event extreme?
I think it depends. It depends a lot on the science application. I think Dahlia certainly knows about one of them being landslides, and but
Sure, I think yeah, exactly. I think the amount of rainfall it takes to trigger a flood or a landslide, and what the threshold for that extreme rainfall is, I think is regionally dependent and application dependent. So I don't think there's one threshold, but if you're looking at the 99th percentile, 95th percentile, I mean, we're talking about a lot of rain. That's the qualitative answer.
Right, it is definitely.
Yeah, so the absence of rain is something we're also interested in.
Absolutely, yep, and that's where on CoCoRaHS we're always encouraging people to submit your zeros, because drought scientists are very interested in zero precipitation as well. We've got a question from Michael asking, will the data derived from the TRIM precipitation radar be sufficiently quote-unquote real-time to be used for forecasting and warning of inclement weather and flooding, or are additional data sets and modeling required?
I can take that.
This is Walt. That's a good question. So, currently the TRIM data are used in quasi, real time as it's collected. So you get roughly 2 overpasses a day at a given location from TRIM. They use the data right now, for example, at the hurricane centers to fix tropical cyclone centers. Also, you can use the TRIM data for getting some information on the intensity of the convection into developing cyclones. All that information is actually assimilated into current forecast models for tropical cyclone predictions and actually even for weather forecasting. So I think the data are used in what real time in the sense that, when you've got an overpass, you can use the data. And trim will go on will overlap. I think the estimate now is for at least a year with GPM.
Okay, thanks, Walt. Are there plans to conduct a study similar to iFloods anywhere else? And this particular person is asking, pretty please, in Western Washington. So, any more field campaigns? Yeah, but are there any more field campaigns in plan? Yep.
Yes. There's a campaign planned actually next year, similar to this, actually with aircraft also in North Carolina, to start dipping our toe in the waters of topography. And then actually, oddly enough, we are planning on going to Washington State in the end of 2015, actually, beginning of 2016, to look at the heavy flooding rains and really snow in the Olympics along the Olympic Peninsula. That'd be somewhere in the November to January timeframe of 2015, 2016.
Great. Well, thanks. Yeah, we have a couple other questions about any more plans to do studies out west. Another person in Idaho is curious too, but that's good news that we've got more field studies planned, and hopefully CoCoRaHS can be a help to that as well.
Sorry, just to interject, on our website, if you go to pmm.nasa.gov, there is a section for field campaigns, ground validation activities and field campaigns, and so you can see what's been done in the past, and hopefully we'll have some information on future campaigns as well, so you can see what we've been doing.
Great. Okay, well, it is 8:30 on the East Coast, and we're going to go ahead and wrap things up here. There were one or two more questions that came through, but we will forward them on to the presenters, and if there's a possible answer, then they will email you directly with the answer. So there's just one or two more questions that we didn't get to, but we will email you after the fact. So thank you again, and to remind everyone that as soon as you exit the webinar, if you could give us just 2 more minutes of your time to fill out the poll, we would really appreciate it. So thank you again to Dahlia, Dorian, Steve, Walt, and Ricardo. We really appreciate your time and your expertise.
And thanks to you guys.
Yeah, thank you very much.
And thanks to you guys. Yeah, thank you very much.
Great. Okay, well, goodbye, everyone, and thank you again.
Thank you very much.